These are the slides to accompany Chapter 9, Equilibria, from your text. We're actually going to cover this a little bit differently than your text does, so bear with me as we're a little bit out of order. We're going to start with 9b, and we're going to cover 9c completely differently than your text does. Anyway, we're going to start with 9b, which discusses chemical equilibrium because it can inform most of what we talk about in section 9a as well. We all know from our Gen Chem that if we have a reaction in the form AA plus BB goes to CC and DD, we can actually define an equilibrium constant as is shown on the screen. That equilibrium constant is helpful for all sorts of reactions, some of which have very special definitions, and your text actually talks about some of those definitions. Remember that whenever we define these equilibrium constants, the only concentrations that we actually include are mole-based concentrations or partial pressures. We never include concentrations of solids because they're not concentrations, and we never include solvents either. So when we, for example, are looking at the dissociation of water, we're going to see that we don't have to include anything in the denominator since water is the reactant and it's the solvent. So we have a Kw that then equals the hydronium concentration plus the hydroxide concentration. So we've given that a very specific type of K value, but it's the same as any other equilibrium constant. We do a similar type of thing with a solubility product. We know that the reactant is a solid, and so we don't need to include that. We just have a product that ends up being the two solubilized concentrations. Of course, we'll also talk about acids and bases in this chapter, and we have an acid dissociation constant and a base association constant, both of which are defined Ka and Kb. We almost always will use the acid dissociation constant and almost never the base dissociation constant. And we can find one from the other using the Kw, but again, usually we just define the reaction in terms of the conjugate acid instead. Easier that way. There are other ways that we can do equilibrium constants as well. I would note that your textbook talks about Kd being as a distribution constant. Usually I've seen that as KOW for the distribution between octanol and water. That's a really common way that we do distribution between organic and water components. Usually you don't use Kd for that. Kd is used for a specific type of dissociation reaction. So with that background, we can start to talk a little bit more about what's actually going to happen in solution with regards to equilibrium. So we know that our solutions can have a number of different things present. We could have compounds that are nonpolar. We could have compounds that are polar covalent. We could have compounds that have hydrogen bonds or weak ionic bonds or strong ionic bonds. Of course, we know that water is polar covalent and it has hydrogen bonds and it has weak ionic bonds when it dissociates. And so water can really dissolve these types of things pretty well. We're going to focus our discussion of electrolytes and a lot of analytical chemistry on things that have weak ionic bonds because those things can actually be electrolytes. Electrolytes form when ions dissolve in water, and so we have weak ionic bonds are going to be the types of things that actually will form ions when dissolved in water. When we have strong ionic bonds, they can't be dissolved by water. Water is just going to precipitate out these ionic compounds, and so therefore they won't be able to conduct electricity in water like other electrolytes. We can define electrolytes as being either strong or weak, and that's going to be dependent completely on the ionization, which again is equilibrium driven. Strong electrolytes are going to dissolve completely like salt. Weak electrolytes are going to ionize partially. A lot of organic acids are like this, so the example shown is acetic acid. Any sort of acids and bases that aren't salts are going to be weak electrolytes. So think like ammonia is going to be a weak base, and it's going to be therefore not a salt and a weak electrolyte. If we use something like sodium hydroxide, that would definitely be a salt, and it would be a strong electrolyte instead. Any of our strong electrolytes are going to be salts or strong acids or strong bases. So in order for us to understand what types of things are actually going to be electrolytes in solution and the extent to which they will be electrolytes in solutions, we really need to remind ourselves a little bit of what's going on with acids and bases. So we know that we can have an acid reaction, acid dissociation reaction, that's defined by a Ka like we just talked about. So that's our acid equation. And then we can also have a base association that's defined by a Kb. That's our Kb. Of course, we can also combine these together where we have an acid reacting with a base, and we get the conjugate base of that acid and the conjugate acid of the base. This is the basic Bronsted-Lowry acid-base reaction definition that we've seen often. Whenever we have an acid reacting with a base, we call that a neutralization reaction because the acid and base are both reacting to form less reactive compounds. Some substances can actually be both acid and base. Water is a great example of this. We can have water becoming more acidic, becoming its conjugate acid and therefore functioning as a base, or we can have water going to hydroxide, so losing a proton and therefore functioning as an acid. It can move it back and forth between those. That's generally referred to as amphoteric. We also sometimes use amphiprotic to refer to that, meaning the protons can go either way. Now, we need to realize that when we talk about having H plus or H3O plus, we're really not talking about something that's just isolated in solution. It's something that's always going to be hydrated. So we have a water molecule shown here interacting with an H3O plus molecule here and interacting with other water molecules and other water molecules. All of those are going to interact in complex lattices. So we're never talking about something in isolation. We're going to draw a lot more in that in later chapters, but for right now I just wanted to point out that whenever we're talking about things being dissolved, it's never just one thing isolated in solution. We also need to understand that whenever we have a solvent that's polar protic, meaning that it has a dipole associated with it and it has a somewhat acidic proton, it can actually go through a process called autoionization or autodissociation or autoprotolysis is how your textbook refers to it. Water is the most common example of that. When water reacts with itself, it can split up into hydroxide and hydronium, and we can actually define an equilibrium constant for this as well. We call that the Kw. The Kw at room temperature has a value of 10 to the negative 14th. But water isn't the only substance that does it. We can have things like methanol will give us an auto-dissociation of 10 to the minus 15th, so it does it less readily than water. Acetic acid can actually auto-ionize or protolyse as well, and we end up with a conjugate base and conjugate acid mixed together. I couldn't actually find a K value for that. It's probably about 10 to the negative 16th. And ammonia, even though it's a base, can do the same thing, or primarily functions as a base. It just does so much less readily, so on the order of 10 to the minus 30th. But that means that we're always going to have some ions in solution if we use a polar protic solvent. So let's hone in a little bit more on what actually happens when we mix an acid in with water. There are two different types of acids that we define with strength relative to water as being either strong acids or weak acids. When we have strong acids, we will talk about acids that dissociate completely, so going all the way to A minus and H3O plus in water, meaning that we don't have any equilibrium going back the other way. We've essentially gone completely to products and we don't even worry about the concentrations of reactants because they're so low. Now, a weak acid is always going to be in equilibrium, so we're going to have always some mixture of the HA that we put in and the A minus that we will see in solution, as well as the acid that develops from it. Now, that's great for water. We now know that we can have strong acids and weak acids, but we don't necessarily know how strong the strong acids are. And so while water is able to differentiate the strength of weak acids, we can't use water to do that for strong acids. We have to use a different type of solvent called a differentiating solvent to tell which acids are stronger and weaker. When we use a differentiating solvent, say like acetic acid, which is a stronger acid, it's going to accept the protons from strong acids less readily, and so it might take a really strong acid and dissociate completely, or that really strong acid could dissociate completely in acetic acid, but a less strong acid will be in equilibrium. So we'll see that we move back and forth between having protonated sides and deprotonated sides for a less strong acid. So again, that allows us to differentiate between acids that are strong in water and to develop a relative strength for those. We're going to put a lot more focus on what's actually happening in water with our weak acids, because that's going to be where some of the most interesting equilibrium concentration effects are going to happen. So we know that anytime we have an acid that we put into water, if it's a weak acid, it's going to split up to some extent into H plus and A minus. That means the total acid that we put in, HA concentration total, is going to be the sum of the stuff that actually stays as HA, so over here on this side, the concentration that stays there, and the stuff that turns to A minus. So that relationship will be very helpful in determining what is actually truly in solution, so the actual molar concentrations rather than the analytical concentrations which we put in. Now, we can derive a lot more if we make a simple assumption. The assumption is that any A minus that we have is going to come from the same place as the H3O plus, and so we're going to end up having those concentrations be approximately equal. That makes sense because A minus and H plus are both coming from HA in this reaction. As long as we don't have a very high level of autoionization, we should be able to make this assumption pretty safely. Now, we do have autoionization, so if our A minus concentration falls really low, we're going to run into trouble. This is going to end up not being a true assumption. Or if our pH is different than neutral before we put things in, then we're going to end up having another source of H plus, and we're going to run into trouble there as well. But in general, as long as our A minus concentration or our HA concentration coming in is relatively high compared to the acid dissociation constant, we'll end up seeing this be true. Now we also can use our equilibrium constant, our acid dissociation constant, and use this in relationship to our previous equation and derive some interesting facts. So first off, if we make this assumption that A minus is equal to H3O plus or H plus, we use those interchangeably, we can actually simplify this equation so that we'd say that our Ka is more or less equal to the concentration of H plus squared, substituting in H plus for this A minus, over the concentration of HA. Now again, this is the concentration that's actually present in solution, not the total. That's the analytical concentration. We can substitute in that total though, since that's what we're going to know, what we put in, and then subtract out the pH, or the hydrogen concentration, and that would be equal to that HA, that analytical, analytical minus the hydrogen concentration is equal to the molar concentration of HA. Now this allows us to have something that we know right off the bat, our analytical concentration, what we put in, and H plus, just one variable related to a defined value Ka. We're going to make one other assumption to make this a little bit easier. That assumption is going to be that our HA total, the stuff that we put in, is going to be a lot higher than the hydronium concentration. Now again, this is an assumption that's not always true, but it's generally going to hold true. And if we make that assumption, now we can simplify this. Our HA total is more or less going to be equal to our HA total minus H plus. If HA total is much higher than H plus, that's not going to have a huge effect on this denominator, and we can simplify this. Makes our math a lot easier. We can now solve for H plus, and we know that our acid dissociation constant times our HA total is going to be equal to our hydronium concentration. Now, this only works if our assumptions hold true, but now we have a value for hydronium that's going to have some amount of error to it, but it's going to be, plus or minus 10% in most cases. And so if we have this value of hydronium, we can actually use this to check this assumption, and we can use it to check this assumption as well. We can see that the relative error is going to change for these assumptions based on the log of the CHA, that's a different way of saying the analytical concentration of that acid, the total concentration that you put in, divided by the Ka. So as long as our concentration of our acid is much higher than the Ka, we're going to actually have relatively low error. We're going to be in this region of the graph where we have less than 5% error. Now, another important set of calculations that we do in this chapter is understanding what's going on with buffers. Now, I'm changing the way that we're discussing this completely because I think it's a lot easier to deal with buffers from the mindset of the Henderson-Hasselbalch equation. So again, we're looking at our HA goes to H plus plus A minus. That's our equation. We have an acid dissociation equation that follows that, our products over reactants, defining the equilibrium constant. We can modify that equilibrium constant pretty easily. So we can say, I'm going to take the negative log of each side. That's because once we take the negative log of each side, as shown right here, we can actually simplify it to be negative log of H plus minus negative log of this piece. We can split up the negative log right along like that. That's a normal type of logarithmic math that we do. And then we see that negative log of Ka is the value that we define often as pKa. The negative log of H plus is the value that we define as pH. So now we've got a ratio of our conjugate base to our conjugate acid that's going to be related very closely to our pKa and pH. So this is a very usable form of the acid dissociation equation. Turns out it's actually the same equation, we've just rearranged it to make it more usable. But it's the same thing. These are the same equations. So if we take this equation and think about buffering capacity, we know that we are going to have, when these are exactly equal, A minus and HA, we're going to see that we have the negative log of 1. Now, you might not remember logs exactly, but if you plug that into your calculator, you'll find that when A minus is equal to HA, then we'd see that that whole value is equal to 0. So whenever we have a ratio of this as an indicator of A minus, this is an indicator of HA, the log of that ratio when they're equal is 0. We'll see then, if we're at this point where we have a ratio of 0 here, or a log of 0, we'd see that the pH is going to be equal to the pKa. This is the peak of our buffering region, because any variation that we make to the HA and A minus up here is going to only change things a very slight amount. So we're going to see that A minus, if it goes up just a little bit and HA goes down a little bit, it's not going to change this ratio a ton, and so then we're going to still see that the pH is going to be roughly equal to the pKa. But the more we change that ratio, the more we move outside of this buffering region. And so if we move in either direction, having more A minus or more HA, we're going to see a much larger change to the pH. pKa is never going to change. We're going to see the change in the pH. And so we can see that there's a relationship between the ratio of A minus and HA and how much we can actually change the pH. That's called the buffering capacity. Now we'll also see that depending on where the pH is, that's going to tell us a little bit about what's actually present in solution. So if we look at pKa of 4.74, just as an example, at the point when our pH equals our pK, we'll see that we'll have the exact same concentration of A minus as we do of HA. So this graph would indicate the presence of HA, the black line. The blue line would indicate the presence of A minus. When we're at the pKa, they're exactly equal. Notice that we're going to start to have those the concentration of HA fall as our pH rises above the pKa, and we're going to see the concentration of A minus increase. Vice versa is also true. When we have the pH fall, we're going to see more HA, and we're going to see less A minus. So this can be really helpful for defining what's actually present in solution as well. This works particularly well when we have a pK that's close to pH, and so it's really good math for buffers. It's not as good for other types of systems where we have a drastic difference between these two species, A minus and the HA. Then it's better to use the original acid dissociation equation. Anyway, hopefully that will simplify some of the math that's covered in your book and make it a little bit easier to follow and be helpful to you.